here. Alright, let us look at this example again. So this example is important. That this is the example that and we have j equal to 0 to infinity, have x squared plus r u squared and dt, right? Okay, we all agree that now if a less than 0 and r going to infinity, then let us go into a feedback u equal to fx. Then f we're going to become 0. Agree? We know that. There's one reason. Because for this system, if we don't have f, assume we don't have f, then x dot equal to ax, right? Because a less than 0, that x going to 0 when t going to infinity, right? This is a stable system. So if I have f equal to 0, that means u, I don't have u, x dot equal to ax. If I tell you I don't use my control energies. If I tell you that means r equal to infinity means what? Don't use control energy. I mean, for this case. If I don't use my control energy, that means my control gain equal to 0. For stable system, if control gain equal to 0, that means you just let the system decay by itself. Right? So that makes sense. You understand? That's a physical meaning. But if a larger than 0, that's it. That is unstable system. Now, if r going to infinity, does that mean f 0? If that unstable, r going to infinity, can I conclude that f also larger than 0? No. Because you do that, then this system going to crazy. So physically, that makes sense. If my t going to infinity, a less than 0, then t going to infinity, x going to 0 anyway. So I don't even have to have control. Unless you say, okay, but that doesn't meet my performance. If you say that doesn't meet my performance, then you can allow me to use some more control energy. True? That means your R is not, if the R is too large, then your performance may not be able to meet your goal. Agree? So when you decide how much R you need to be, depending on how much performs. we're asking. If you need more damping than this, more damping than this, then you cannot, then R too large. Agree? R has to have some value, not infinity. Has to be smaller, maybe much smaller. You want to have a lot of damping. Okay? So that just explains that the some physical meaning of this. So we know that from this problem, the solution is unique. Control solution again is unique. All right. Now let us look at the that's multiple degree freedom now, and I already show you that for single spring system, M is a scalar and K is a scalar. Agree? All right. Now, then we can write in terms of this. So system energy will be kinetic energy plus potential energy, and that you can write in terms of this. If M is not 1, is not scalar, K is not scalar, then you can write in terms of matrix. Then this is M can be a matrix, K can be a matrix. Well, we know that M larger than 0, K larger or equal to 0. We talk about that quite often. That's the system energy for multiple degree freedoms. Now we are talking about the matrices. Careful about matrices. All right. Now, if we generalize the system energies, if you look at this, there's no couple. W dot here, W dot here, W and W there. There's no couple, right? There's no W dot W or W dot. We have a kinetic energy and potential energies. But here we have W with W dot, W plus this W dot, right? So if you look at this, then we can generalize the system energies become this. You just add two more terms. One is this terms, one is that terms, and then we create a Q, we call Q. Q11 can be M, Q22 can be K. If you look at only system energies, then Q12 equal to 0. Q12 transpose equal to 0. Alright? And then you have Q11 equal to M and Q22 equal to K. So if you open the optimal control book, your definition of index will be much more general. And that's the definition of the control energies. Called weighted control energy called R. All right. So if you want to look at the a general system, now AC will be a matrix. BC will be a matrix too. So now AC and BC, we talked about that a lot because this is a simple state space model. AC can be 2 by 2, can be 4 by 4, can be 10 by 10. In general, that for any mechanical system, AC will be an even number. Will be 2, 4, 6, 8, or 10. It cannot be odd number. That's a mechanical system. For the control law, U equal to FCX, the same thing as the scalar case. That minimize cost index. Now, the cost index is the generalized system plus weighted control. Here. The generalized the Q. So now the Q here is very general, and that's the optimum control index. The Q, the X dot, if you look at the X dot, the X, T, Q, X, look at these terms, and that is include, we have, if you look at that, we have Q is equal to Q11, right? Q11 and Q12 and Q12 transpose and Q22, right? Like that. X transpose and X. And this X, well, we can write this way like that if you want. Q11, Q12 transpose, and Q22, and this is nothing but W and W dot. Upside down, I think I made upside down. That's okay. This is normally we write like this, but I think the last slide I write it upside down. Last slide, if you look at last slide, they said, because I think I got upside down there. Can you look at back? Look at back. Back here. Okay. No, that's true. Okay. All right. Okay. Now, what I try to explain here is this. If that means this Q11 can be a stiffness matrix, Q22 can be a mass matrix, like that. This is more general in terms of my total, we call the total generalized system energies. So that is the half, the J there, if we look at J here, J there is half from 0 to infinity, then that's Qx plus U T R U then dt, and then this is, as a matter of fact, this include the kinetic energy and potential energy. That if this equals 0, that equals 0, that means I have this J is nothing but the system energy plus control energy. Alright, so here, now, Q is not equal to 0, and R has to be positive definite. Then there, if you look at carefully, R cannot be 0. Because that requires positive definite. Q can be 0, and R cannot. So you have to be careful here. Now, if you look at carefully here, that Q, I say large or equal to 0, means this is semi-positive definite, and this is positive definite. You know why? You know why? Any reason for doing this? Huh? Because what? Because J must be larger than 0. J cannot be negative. J